Alright, let's take a look at a couple examples of indeterminate products now that we've introduced what those are. First up, we're going to try the limit as x approaches 0 of the sine of 5x times the cosecant of 3x. First thing to note is if we attempt to use the direct substitution property, as x goes to 0, the sine of 0 will be 0, but as x goes to 0, the cosecant of 0 will approach infinity. So our two options for what to do with this, if we're going to force a fraction, would be the following. We can either do the limit as x goes to 0 of the sine of 5x divided by the reciprocal of the cosecant of 3x, or we could set this up as the limit as x goes to 0 of the cosecant of 3x divided by the reciprocal of the sine of 5x. Now, each one of those has their advantages and disadvantages. The big thing that I want to point out, though, is when we're taking reciprocals of trig functions, we have something for that. The reciprocal of the cosecant, for example, would be the sine. So we could express this as the limit as x goes to 0 of the sine of 5x over the sine of 3x. This one over here we could express as the limit as x goes to 0 of the cosecant of 3x over reciprocal of sine would be the cosecant. Now, given the option of either differentiating a sine function or differentiating a cosecant function, fingers crossed that you would be doing the same thing that I am, which is going with the sine function. If we attempt to use the direct substitution property on this bad boy, we're going to wind up with 0 divided by 0. That means that we would be allowed to use L'Hopital's rule and differentiate the top and differentiate the bottom. This would be the limit as x goes to 0 of derivative of the sine of 5x would be the cosine of 5x multiplied by the derivative of the inside by the chain rule. So cosine of 5x times 5. Denominator is going to look very similar. This will be the cosine of 3x times an extra factor of 3. At this point, if you attempt to use the direct substitution property, good things happen because the cosine of 0 is equal to 1. This will be 1 times 5 over 1 times 3 for a final answer of 5 over 3. Now, there were some limits from back in Chapter 3 that would have allowed us to do this in a slightly different fashion, but this seems to be the more straightforward fashion. Next example, we're going to take the limit as x goes to infinity of x to the third power times e to the negative x squared power. Now, when it comes to a limit at infinity, we can't exactly plug in infinity, but x cubed will go to infinity, and e to the negative x squared will essentially be e to the negative infinity, which tends toward 0. This gives us our indeterminate product. The thing I want to point out for this, though, is if something is already a negative exponent, there is really only one logical way to deal with this. That's to take the negative exponent and move it down to the denominator. So that'll go into the denominator as e to the positive x squared. I'm not saying that you can't force the x cubed into the denominator. I'm saying you really don't want to. At this point, as x tends toward infinity, your numerator is infinity, your denominator is infinity. This allows us to use L'Hopital's rule. L'Hopital's rule says take the derivative of the top. Derivative of x cubed will be 3x squared. And the derivative of the bottom is going to require the chain rule. Derivative of e to the is e to the, and then we'll get an extra factor of 2x from the derivative of the x squared. Now, still technically in the form infinity divided by infinity, but it's going to be to our benefit to go ahead and do a little algebra and reduce one factor of x from the top and bottom. Otherwise, our next derivative would involve the product rule in the denominator, and we definitely don't want that. Now, it's still in the form infinity divided by infinity, so I'm going to go ahead and apply L'Hopital's rule one more time. Differentiating the numerator, derivative of 3x is going to give us 3. And derivative of the denominator is essentially going to be the same as before, just with an extra factor of 2. In this form, your numerator is 3, your denominator is tending toward infinity. And because the denominator is tending toward infinity while the numerator remains constant, this thing tends toward 0 for a final answer.